Alright, now we're going to talk about the radio frequency pulse. What is a radio frequency pulse? It's an electromagnetic radiation with electric and magnetic field with the same frequency range as of the precessing protons. So it has to be at the same frequency range. There are two important things that happens when you apply the RF pulse. The first is the energy absorption. That means the more protons line up in the anti-parallel direction. The second thing is the phase coherence. That means the RF with same frequency causes phase synchronization of the precessing protons, and we'll take an example of that. So let's first check out the concept of energy absorption, and this essentially is going to be effect of RF on the longitudinal magnetization. So again, this is the magnet and all these are the protons. So as you recall, there are more protons that line up in the parallel direction rather than the anti-parallel direction. Once you give RF pulse, because now they have more energy, so some protons gonna line up in the anti-parallel direction. So the net effect will be that there are more protons line up in the anti-parallel direction, and that's gonna decrease your longitudinal magnetization. The second effect is phase coherence, and that's going to be seen as the effect of RF on the transverse magnetization. So again, the protons are precessing in the magnetic field, which is the external magnetic field, but there is no RF pulse yet, but they are precessing randomly. They are not coherent. Once you give the RF pulse, they start to precess coherently, and that's going to increase your transverse magnetization. Looking at the same thing from a different perspective, it's like looking from the top. Again, no RF pulse yet, so there is more longitudinal magnetization and the precession is incoherent. Once you give the RF pulse, the LM is going to be decreased, and all the protons, they're gonna start to precess together. That's gonna increase your transverse magnetization. If you put all those protons together and just look at the NMV, which is the net magnetic vector, then it's gonna look like initially is this, no RF pulse. Once you give the RF pulse, it's gonna start to precess, and then eventually the precession is going to be coherent, so it's going to look like that. It's only moving in the transverse plane. So again, if you look from the top, it's going to look like your NMV is moving in the transverse plane. It's just very coherent movement. And if you look from the different point of view, using your z-axis and the xy axis, so once you give the RF pulse, initially your NMV is in the z-axis. Once you give the RF pulse, your NMV is going to flip to the xy plane, to the transverse plane, and this angle, because it's turning 90 degree, so it's known as 90 degree RF pulse, and 90 degree is your flip angle. That's the concept of flip angle. So again, the summary of RF pulse is you get energy absorption where more protons line up in the anti-parallel direction, so that your LM becomes 0. The second concept is you get phase coherence. That means RF with the same frequency causes phase synchronization of the precessing protons, and then you get more and more of transverse magnetization. Let's quickly learn the concept of resonance. Resonance is an energy transfer when an object is subjected to a frequency the same as its own. So now we know that we have a net magnetization in the transverse plane. So you put a receiver coil in the transverse plane. The NMV in the transverse plane passes through the coil, and then you get voltage induction, which is going to be converted to give you the MRI signal. So again, your NMV is rotating in the transverse plane. You put a coil in induction coil, and then you get the MRI signal. All right. So that's it